Good morning to all of you. I am Dr. Jigar Patel. Today topic of my presentation is physics of ultrasound. We will see first definition, then interaction of ultrasound wave with tissue, then followed by various type of ultrasound we are using in imaging. First, the definition of sound. Sound is a mechanical and longitudinal vibration that transmit through a medium. Elastic medium must be present to travel for the sound. Sound cannot travel in vacuum. Here, as you can see in the image, particles of the medium vibrate parallel to the line of propagation, and the band of compression and rarefaction is developed in the medium. So basically sound require medium to travel, and the sound wave travel longitudinally in the medium. Now, as a part of wave, sound is a mechanical and longitudinal wave. Other type of waves like electromagnetic, which doesn't require any medium, and the types are light, X-ray, radio and infrared. Now, ultrasound is a sound wave with mechanical and longitudinal wave with frequency more than 20,000 Hertz, which is exceeding the upper limit of human hearing. So there is a chart which show the hearing range is 20 to 20,000 Hertz, and more than 20,000 Hertz is called ultrasound. Certain animals like bats use it for navigation purpose, and sound below 20 Hertz is called infrasound. Animals like elephant use for navigation purpose infrasound. So ultrasound frequency for medical purpose is or diagnostic imaging is in the range of 1 to 20 million Hertz, and this technique is also known as pulse echo technique. Now, on the history part of ultrasound, animals use ultrasound for navigation and detection purpose since millions of years. But commercial use is first done in 1937 by Sokolov to use for detecting flow in matter. And during Second World War, sonar, which is a short form of sound navigation and ranging, used by submarines to detect enemy ships. Later on in 1950, ultrasonoscope used for medical diagnosis in Japan. And in 1953, Dr. Helmut Hertz and Dr. Adler used ultrasound to examine the heart, and it is the beginning of clinical echocardiography. Later on in 1970, Dr. Lee Prezin, a cardiologist from Chicago, used M mode in transesophageal probe, and it is the origin of TEE. Now, when we compare ultrasound with CT, MRI and chest X-ray, apart from basic difference of mechanical wave and electromagnetic wave and require medium for transmission, ultrasound has a great advantage, like you can do real-time imaging in non-invasive way without ionizing radiation, with low cost and wide application, with mobility and flexible imaging. You can also do biopsy with the use of ultrasound. So ultrasound provide great benefit at very low cost compared to CT, MRI and chest X-ray. Now we will see the fundamental properties of ultrasound, like amplitude, velocity, wavelength, period and frequency. First one is the amplitude. Amplitude is the strength or intensity of a sound wave at any given time. It indicates as a height of the sine wave above or below the baseline. Its unit of measurement is decibel. So by US FDA, maximum allowed intensity is 720 watt per centimeter square to prevent tissue damage like cavitation and thermal injury. It is around 180 decibel when you convert it in this. For the lithotripsy, we use high intensity sound signal to fragment renal source. So amplitude will indicate brightness of the image. So if wave has high amplitude, you will get brighter image, and if wave has low amplitude, then you will get darker image. Second important property is velocity. Velocity or propagation velocity is the speed of the sound wave that travels through a medium. So it is measured in centimeter per second, and this propagation velocity depends on three factors. First is the stiffness of the medium. So if medium is more stiff, then it will transmit the sound wave faster. Similarly, if the density is it also depend on density. If density is higher, then there is no space to move the molecule, so it will decrease the speed. And third is the temperature. Temperature increase will increase velocity of the sound wave by increased movement of the molecules. So in the human body, temperature will remain constant, so it will not affect. but stiffness and density wise it will increase or decrease velocity. So as you see in this image, lower image, sound wave travel faster in solid and slowest in air or gas. In the human body, average velocity is around 1540 meter per second. So most of the tissue sound wave travel at the rate of 1540 meter per second. So we take as a reference speed. Third important point is a wavelength and period. Wavelength is a distance between two bands of compression and rarefaction. It is a measurement of distance to complete one cycle. It is measured in millimeter or centimeter and it indicated by lambda. While the wavelength is a distance, but the period is the time taken to complete one cycle. So it is measurement of time and measured in second. So this wavelength and distance depend on velocity or frequency. So as per the velocity equation, velocity is the product of frequency and wavelength. So frequency and wavelength is interdependent. So if one increase, then wavelength will decrease, or if frequency is decreased, then wavelength will increase. So this wavelength will determine the resolution of image. So if the wavelength is decreased, then it will interrogate more molecules and you will get better resolution. So to improve image quality, you have to reduce wavelength by increasing frequency of the probe. Fourth important point is frequency. Frequency is the number of wavelength per second and it is measured in a hertz. So 1 hertz is equal to 1 cycle per second. So cycle is the time to complete one frequency, but one wavelength, but the frequency is the number of cycles per second. So for the audible sound, it is range between 20 to 20,000 hertz. So you can see in the image two different frequency in above image. One has a higher frequency, one has a lower frequency, and velocity will be same in both the medium. So if frequency is increased, then wavelength is decreased. So frequency is inversely related to wavelength. And the last important property is acoustic impedance. It is the resistance that material offered during the passage of sound wave. When sound wave travel in any medium, it will provide resistance. So it is calculated by multiplying density of the medium and the speed of the wave. So density will affect this impedance. When your density is increased, then impedance is increased, and it works in both the way. When sound wave travels and receive, in both way this impedance effect, and it indicates the sound transmission capacity of particular medium. So more denser medium like bone, muscle have a higher acoustic impedance, as you see in this chart, and air and fat which have lower molecular density have a low acoustic impedance. So reflection occurs due to difference in this acoustic impedance difference between two tissue. So this is why we can't get good image in transgastric TE image, because there is air in the fundus. It will and when air and the tissue both the medium affect the this image transmission. Similarly, this is the reason why we can't get good image in upper esophageal view, because air filled lung and left bronchus will have a different acoustic impedance than a tissue. So it will reflect all the image and image will not properly form. This is the reason why transducer must be in a direct contact in skin without the air. So we are using acoustic coupling gel for better transmission of the sound wave. Now sound wave when transmit in the medium, it interact with the tissue, and part of it attenuate, part will absorb, part will reflect, and part is scattered. Some of the distance part will refract and diffract also. We will see one by one. First one is the attenuation. Attenuation is the reduction in the amplitude and intensity of sound wave. It has three components. First is the absorption, scattering, and reflection. So it is decreased amplitude of the and intensity of sound wave when it travel to any medium. So it depends on two factors. First is the frequency and depth of the medium. So if the high frequency sound wave will travel in the medium, it will attenuate faster than a low frequency. So to get better imaging at the depth, we have to use low frequency, so it will less attenuate than the high frequency. Similarly, at the depth of the medium increase, it will more attenuated. So attenuation coefficient is the measurement of attenuation of any medium. For the most of the tissue, it is 0.5 to 1 decibel per centimeter per megahertz. Gas and fluid have a very low attenuation coefficient, so it will allow them to pass, and bone has a very high attenuation coefficient, so it will block the sound wave. Second interaction is the reflection. It is the basis of all ultrasound imaging. So image will form by this reflected echoes. So it is the main reason why we get the ultrasound image. So it depends on angle of incidence. If angle of incidence is 90 degree, you will get more reflection. And the size of reflector. If it is smaller than the wavelength, so it will not reflect. But if reflector should be more than the wavelength of the sound wave, so it will reflect the image. Third important point is the acoustic impedance. So if there is a more acoustic impedance between the tissue, then you will get more reflection. This reflection is of two types. First is the specular reflection. It is a mirror-like reflection from large and smooth interface. So when sound wave travel in the tissue, and if it got this highly reflective surface, like you can see in the image, there is a diaphragm which is at the 90 degree of the image, and you will get a high strong reflection, and it is hyperechoic. So here angle of incidence and angle of reflection is similar, so it is a angle dependent reflection, and the interface should be bigger than ultrasound wavelength, so it will reflect properly. Second type of reflection is a diffuse reflection. It is also known as Rayleigh scattering. Here reflection from small, irregular and rough interface within a solid organ. Here the reflector is smaller than ultrasound wavelength. Here angle of incidence and angle of reflection is not same, it is different, and reflected echo are very weak and known as backscatter, and they form characteristic pattern of the texture of solid organ and tissue. So if the in the image there is a vascular component, then there is no reflection and it will show as a isoechoic, and other part of this diffuse reflection form the texture of the organ, so it will reflect as a hypoechoic or weak reflection, and you can see as a gray dot in the image. They form inhomogeneous granule signature in the speckle of the myocardium, and this pattern can be tracked in cardiac cycle, and it is the basis of speckle tracking to assess the regional wall motion. Third tissue property of this sound wave is the refraction. It is the change in a direction or bending of the sound wave. When wave pass from one medium to another at an acute angle, it is refracted, and this refraction is depend on the velocity of sound in a two medium. If velocity is equal in the both medium, then there is a no refraction. In the human body, the average velocity around 1540 meter per second, so it is not important, so it can be ignored. But this refraction property used by acoustic lens to focus the beam and improve image quality. Similarly, this refraction will cause artifact in the lower part of the image. Fourth property is the diffraction. It is the change in direction of wave as they encounter obstacles or aperture. Because of this diffraction of the sound wave, we can easily hear around the corner and through open windows. Now this image shows basic part of any ultrasound machine. It has monitor to display image, transducer to transmit and receive the ultrasound, keyboard to entering data, pulse control to amplify and measure all the data, CD and DVD drive to record the data, and onboard computer to process the signal. But the most important part here is the transducer. Let's see it. Transducer has a plastic housing and it functions to convert an electric signal into ultrasonic energy that can be transmitted to tissue and vice versa. In the anatomy of this transducer, the proximal most part is the acoustic lens, which used to refract and focus the beam. After that, there is a acoustic matching layer. It is a thin layer of material which provide better sound transmission, and it reduce acoustic impedance difference between transducer and tissue. Its thickness is 1/4 of wavelength of this particular sound energy. So it will provide better sound transmission and receive. After that, this acoustic matching layer is the piezoelectric crystal. We will see in later slide, and behind this piezoelectric crystal there is a backing material. It is made of rubber and tungsten, and the purpose of this is to reduce vibration of the element which don't take part in the beam formation. It shortens the spatial pulse length and pulse duration and improve the axial resolution of the system. It is similarly like placing your hand on a ringing bell. It works like that. Now the piezoelectric effect. Our piezoelectric crystal will produce piezoelectric effect. It is first described in 1880 by these two gentlemen, Pierre Curie and Jacques Curie. So this piezoelectric effect is the on application of mechanical force, certain material generate electric charge. And the reverse of this effect is also true, and it is known as reversible piezoelectric effect, in that when applying electrical field, certain material change in shape. So this piezoelectric word is derived from Greek word, where piezo means to press and electron means amber fossilized organic plant which used in electric study. So piezoelectric crystal will produce piezoelectric effect which will use for sound wave production, ultrasound wave production. Now these piezoelectric crystals are naturally occurring like quartz and tourmaline, but synthetic use in medical ultrasound is known as ferroelectrolytes. PZT is the short form of lead, zirconate and titanate. Here, when, as you see in the image, when voltage is applied to this crystal, they will realign and change the physical dimension of the crystal. So if voltage is applied in pulses, then crystal vibrate and produce sound wave. Similarly, when the sound wave received by this crystal, they change their, they produce electric charge, and it will help in production of image. Now important point is Curie temperature. It is the temperature at which this polarization is lost. So heating this crystal make them useless. So transducer never be used in, never be autoclave. Now sequencing of event for production of ultrasound wave is the ultrasound transmit high frequency range into 1 to 12 megahertz sound pulse into the body. So the sound wave travel in the body and hit a boundary between tissue, and some of the sound wave reflect back to the probe while some travel further. The reflected wave are detected by the probe and relayed to machine. And the system calculate distance by this equation. Velocity is equal to distance into time divided by 2. 2 is due to sound transmission from transmission and coming back, that's why divided by the 2. Here velocity is in tissue is a fixed is as a 1540 meter per second. So distance is calculated by time. So machine display the distance and intensity of the echoes. Now goal of an ultrasound system is to make like tissue look alike and unlike tissue look different, and it depends on three factors. The first is the resolution of the system. Resolution of the system is of three types: axial or lateral resolution, contrast resolution and temporal resolution. Second is the beam formation method, how system will focus and scan the area. And third is the processing power. It is ability to capture, preserve and display the information. We will see them one by one. First is the resolution of the system. So it is first axial resolution or lateral resolution. Axial resolution is the ability to differentiate two objects that are very close but at different depths along the long axis of the beam. So this axial resolution depends on the frequency and wavelength of the sound wave. So high frequency, as you see in this chart, with 10 megahertz of frequency, the wavelength will be much more, around 0.1 mm. So the resolution, axial resolution of 0.1 mm. So you can identify tissue with 0.1 mm of accuracy. When this frequency is decreased, then wavelength is increased at the cost of this axial resolution. But this axial resolution leads to higher frequency, and this higher frequency has attenuation. So with high frequency probe, this axial resolution increase, but depth of the investigation decrease. So with 10 megahertz of probe, you can visualize up to 6 centimeter only. Similarly, lateral resolution is the ability to differentiate two objects that are very close at the same depth along the long axis of beam. It depends on the width of the ultrasound beam, number of channels in the system. If number of channels increase, then you will get better lateral resolution. And the third is the depth of the object. So at the focal zone, there is a maximum concentration of ultrasound beam, so you will get best resolution at focal zone. You can adjust this lateral resolution by controlling gain and focusing. Second is the contrast resolution. It is the ability to differentiate two adjacent objects of similar intensity and reflective property as a separate object. It is the tissue differentiating capability which provide critical diagnostic information. As you see in the image, in liver with metastasis, both have a normal liver and metastatic liver have a same reflective property, but due to contrast resolution we can differentiate between them. Last is the temporal resolution. It is the ability to accurately locate the position of moving structure at the particular instant in time, like the valve motion or heart contraction. It is also known as frame rate or sampling rate. So it depends on pulse repetitive frequency or sampling rate. So if you increase this sampling rate, you will improve temporal resolution. Similarly, second factor, it affects depth of scanning. If you scan in the more depth, then it will reduce the frame rate and it will reduce the temporal resolution. Similarly, sector width also affect that. If you your sector width is very wide, so it will reduce the frame rate and reduce temporal resolution. So to get better temporal resolution, you have to reduce the depth of scanning and sector width. Now resolution and penetration has a trade-off. When resolution increase and then penetration will decrease. So when you use high transmitter with high frequency, it will increase the resolution axial and lateral, but reduce the penetration due to attenuating loss of the sound wave. So there is always compromise between resolution and penetration. So to visualize deeper structure, you have to use low frequency probe, but it has a poor resolution, and to shallow structure you have to use high frequency probe. Now this is some common type of ultrasound probe we are using. First one is a linear array. It has high frequency around 8 to 15 megahertz, and so high frequency your depth of imaging is superficial around 1 to 4 centimeter, and we are using for vascular nerve block and biopsy. Second one is the sector or phase array. It has lower frequency range around 2 to 6 megahertz, and for depth of imaging around 4 to 8 centimeter. We are using it for TE and cardiology purpose, transthoracic purpose. Third common type is a curved linear array. Here frequency range is higher, between 2 to 12 megahertz, and the depth of scanning is between 2 to 6 centimeter. We are using for ultrasound of abdomen and thorax this type of probe. They all have a currently focusing method of electric phasing, and scanning method is electronic sequencing. Now we will see the various modes of ultrasound. The first one is the A mode. It is known as amplitude mode. It is the most primitive mode. It is static one-dimensional mode and simplest display mode. Here signal displayed as a spike on a graph. A spike height is proportional to the intensity of the reflected sound. Here as you see in the image, it is used in ophthalmology. It is known as A scan. So here in the vertical axis will show the amplitude of the returning echo, and horizontal axis indicate depth in the patient. Second mode is the B mode. It is known as brightness mode. It is the most popular mode of display. It provides structural and functional information. Here, ultrasound send multiple beams in the tissue and returning echo display as a dot, reflective surface as a dot. Here we use brightness of the dot proportional to the strength of the echo, and 256 shade of gray is used. It is also known as grayscale imaging. And 2D image is built by rapid repetitive scanning in a fan shape area. This is 2D imaging, it is real time beam mode imaging. Here what happens, each pulse of PZT produce vibration and produce single line of information, and there is a multiple beam system generate pulses of around 128 scan line of information. Full sweep of this beam across the plane when processed and display is called a frame. And acquiring, processing and displaying frame at a rate of 30 frame per second produce real-time dynamic image of the heart, as you see in the lowermost area. It has less temporal resolution than M mode, as the frame rate is around 30 to 60 per second. Third mode is a M mode. It is also known as time motion mode. Here brightness mode with time and as a reference. Here signal reflected by the moving structure are converted into waves and then displayed continuously. Here time is on the horizontal axis and depth of the scanning is on the vertical axis. Here high sampling frequency, around 2000 scan per second. So you will got the perfect timing in cardiac cycle, and it is used to evaluate cardiac wall and chambers. Now signal amplification method are of two types which we are using. First one is the time gain compensation, and another is the simple gain. They both have manual control, and it is used to amplify for the imaging for the better evaluation of the structure. So in time gain compensation, there is a multiple dots which indicate depth of the field. So to improve, to enhance selective, you get selective enhancement or suppression of the sector of the image. So if you want to improve lower part of the image, then you have to slide this dot to the right side. So you will the image will got better enhancement. Similarly, gain is the simple gain is the affect all part of the image and seen as the change in the brightness of the image of the entire screen. So if you rotate this probe, you will get improved brightness in the whole image, not a single part. So these two type of signal amplification method we are using. Now we will see the beam physics. When excitation of this piezoelectric crystal occur, they produce tiny spherical wavelet. And according to the Hughes principle, this waveform merge and produce near, as you see in the image, there is a near parallel constructive wavefront. And the proximal part of this cylindrical portion is known as near zone. It is high intensity zone because there is a highest concentration of ultrasound beam in this zone. So you will get best result image in this near zone. After that, there is a distal or divergent portion, or it is of cone shape, and it is known as far field. It is here the concentration of beam is reduced, and it is you will get the low intensity image in this zone. And the focus zone is the transition zone, where the point it is a point where beam begin to diverge. It is between the near field and far field. Here beam width is narrowest in the focal zone, and you will get best axial and lateral resolution in this focal zone. So this near zone and far zone is depend on the frequency and diameter of transducer. So if the frequency and diameter change, this near field and far field, near field change. So to get best image, you have to use larger diameter of the transducer and high frequency. As you see in the image, with 10 mm diameter and 4 megahertz of frequency, you will get highest near field length, and best image you will get with that as compared to 5 mm diameter and lower frequency. So to get the best image, you have to use large diameter probe and high frequency. Now beam focusing method is the concentrating the beam to the smallest cross sectional area at a focal region to improve resolution. So this ultrasound probe use two type of beam focusing method. One is the mechanical and second is the electrical. In mechanical focusing, there is a two type. Either they arrange PZT in the conical shape, or they use acoustic lens to focus this beam. On electric focusing, it is known as phase array. Most of the newer probe use this electric focusing method. Here, converging the beam at a specific distance by sequential activation of adjacent PZT of the transducer. Here what happens, they fire outer element before the inner, as you see in the image. So with specific time delay, they fire outer element, then inner element. So you will focus your sound wave, and it is a variable. By mechanical focusing, you only get fixed focal length, but by electronic focusing, you can change your focal distance. And this focusing method is also not only during transmission, or it also in the reception also. It is not dynamic reception focus. So they apply time delay in reception to adjacent focus for listening at depth. Now beam scanning is also of two type. It is either mechanical and or electrical. So by beam scanning, you can increase field of vision for smaller probe. So with smaller transducer, you can you can scan large area. So by mechanical method, they use oscillating or rotating wheel, like using an intravascular ultrasound. And electronic has two type: electronic scanning and electronic phasing. In upper part of image, you can see electronic scanning. Here only subset of PZT are successively activated, while in electronic phasing there is a sequential activation of PZT with time delay and allow steering of ultrasound beam. Most of the newer ultrasound probe use electronic scanning and electronic phasing. Now Doppler is used in ultrasound. It is based on Doppler principle. So when you hear sound from the car, when it is come towards you, you will hear high pitch or high frequency sound. But if car is going away from you, you will hear low pitch or low frequency sound. So this is the Doppler principle. So it is first described in 1842 by Austrian physicist Christian Doppler while studying the direction of movement of the star. He describes shift of frequency when acoustic source in motion compared to the stationary observer. So echoes produced by moving tissue and blood cells has a different frequency. So if these blood cells move toward the probe, it will emit more frequency. When receiving, the transmitted frequency is more than receiving frequency is more than transmitted frequency. Similarly, if this red blood cell move away from the transducer, then the receiving frequency is less than transmitted frequency. So you can calculate the frequency shift by calculating receiving frequency and minus it from the transmitted frequency. And this frequency shift determines relative velocity and direction of moving tissue, and it's known as Doppler principle. So you can calculate Doppler shift by this equation. Here the important thing is the cos theta. It is the angle between ultrasound beam and target velocity. So this flow velocity measure most accurately when the beam is either parallel or anti-parallel to the blood flow. As you see in this image, then when when we measured Doppler this velocity at the 0 degree, then you will get the aortic flow rate around 2 meter per second. But if you increase angle by 10%, you will get 1.97 meter per second. Similarly, if increase at the 60 degree, then you will get half of the actual velocity. So to measure actual velocity, the angle should be 0. But and diversion up to 20% can be tolerated with error of less than 6%. And if the angle of observation is 90 degree, then you cannot get the actual velocity. Now use of Doppler, it is used to evaluate and quantify blood flow. Here transducer act as a source and receiver, and flow is a motion relative to the transducer. And you can get the spectral waveform produced by graphical representation of the flow. Here flow coming towards the transducer is above the baseline, and flow traveling away from the transducer is below the baseline. By Doppler, you can get the direction of flow, velocity, either maximum and mean velocity, quality of the flow, whether it is normal or abnormal, and acceleration and deceleration time. Now, when you compare between 2D and Doppler, it has some difference. Like 2D, the ultrasound target is the tissue, while in Doppler you can get blood flow, and the goal of diagnosis in 2D is the anatomy, while in Doppler you will get the physiology of the flow. Type of information in 2D is the structural, while in Doppler is the functional. And for the optimal result, we have to use for the 2D is the high frequency, and angle of interrogation is the perpendicular. So you have to take image in the center of the field. While in the Doppler you have to use low frequency probe and parallel angle of the interrogation, so to get the best image. So both 2D and Doppler both are complementary to each other. Now we will see various type of Doppler which we are using. First one is the continuous wave Doppler. It is continuous and simultaneous transmission and receiver of the signal through separate crystal. Here one crystal is used for emission and one for reception, and here continuous emission. So there is a continuous emission and continuous receive. So there is infinite PRF or infinite sampling rates. So you can analyze high velocity flow with this continuous wave Doppler, but emission and reception are continuous, so computer cannot identify location of emitted wave. So you cannot pinpoint where is the exact point where you get the maximum velocity. So it had no range resolution, but used to quantify high velocity jet and based on this Bernoulli equation. So continuous wave Doppler is very important. Second type is the pulse wave Doppler. Here you use the same crystal to transmit and receive signal. Here there is a base range resolution because the same crystal is used to transmit and receiving the Doppler wave. Here sequence of event is like transducer emit a short burst of the ultrasound wave that targets at the specific depth. And with time delay, this electronic time window open and analyze those echo returning from the sample volume, and this selected echo then extracted, filtered, sample, and Fourier transformation leads to this fractal waveform display. And the duration of gate opening, it depends on the depth in the sample volume. So here very low sampling rate is used in pulse wave Doppler, and it will cause the aliasing. So Nyquist for aliasing you have to understand Nyquist limit. So this pulse wave Doppler sampling phenomena introduce a limit above which the precision of movement reporting is lost. So to measure any frequency shift, you have to sample twice in a one wavelength or one cycle to actual reconstruction of the flow. As you see in the image, the uppermost frequency, uppermost part of the image show frequency of 3. So the Nyquist limit and you observe 11 times, the pulse repeating frequency is 11. So Nyquist limit is the half of the pulse repeating frequency or sampling rate. So if with 11 sampling rate, you have Nyquist limit of 5.5. So you are observing 11 times in this 3 wavelengths, so you will get the actual flow. In middle of the chart, the frequency is increased to 3 to 5, but it is still behind and lower than Nyquist limit. So you will get the actual flow, actual direction of the flow. And the lowermost image, there is increase in the frequency of 8. So it is more than a Nyquist limit, and you cannot identify exact direction of the flow. So in this pulse wave Doppler, this Nyquist limit is very important, and aliasing occur if this frequency shift is greater than Nyquist limit. So aliasing is the false identity, and this appear with a pulse wave Doppler and color Doppler. So both use pulse wave Doppler principle. So aliasing occur in this. Here Doppler sampling rate is too low. So in comparison to the measured blood flow, So the very high velocity, more than 1.5 to 2 meter per second in one direction, incorrectly display as going to opposite direction. So in the pulse wave, you will see the wrap around effect. Here the peak are cut off as you see in the image and display below the baseline. It is called aliasing. It is similar to when you see the car wave, with moving wheel. If the sampling rate is very low, you see the wheel is not moving or stop, but it is due to aliasing. You cannot see the car is moving. So to avoid aliasing, you have to reduce the frequency of the transducer or reduce the depth of the interrogation. So it will increase the sampling rate, and either or you have to use continuous wave Doppler to measure perfect direction of the this frequency shift. Now, third type of Doppler is color flow mapping. It is a combination of 2D and pulse wave Doppler. Here, two-dimensional real-time information of blood flow, direction, velocity and pattern by using autocorrelation technique. You can get multi-glade Doppler technique allow flow mapping. So, which direction is going on with 2D imaging. So, here measuring of the returning echo with sequential at different successive time after transmission of single burst of ultrasound. The disadvantage is that you estimate only mean or average velocity across the beam, not peak velocity. So its use is limited, but you can get qualitative data by analyzing which direction of the flow. So this color flow have two type color used. They use red is flow toward the transducer and blue as the flow away from the transducer, and deeper shade of blue for slower flow and lighter shade of blue has a faster flow. So in normal laminar flow you can identify which direction is flow going, but for turbulence flow we are adding flow variance. They indicate as a green, turbulent flow as a green or as a flame color. So flow variance is used to identify turbulent flow. So for better color flow map, you have to increase the temporal resolution of the image by reducing sector width and depth, and ultimately improving the frame rate. So for better color flow mapping, you have to use smaller sector and lesser depth. Now, color flow Doppler is use pulse wave Doppler technique. So if velocity is faster than the lightest shade represented in the map, you will get aliasing, and it is known as color wrap. So you will get a mosaic pattern. So it is measuring frequency is more than analyzing frequency, and it is aliasing also occur in this color flow map. Second important is the Konda effect. So when eccentric jet, which is appearing smaller than equivalent size central jet, it is due to this asymmetric expansion with vortex-like motion and tendency of fluid jet to be attracted to the nearby surface. So this due to Konda effect, you can misguide by lowering this regurgitation level. It is even with this Konda effect, mild moderate MR will look like mild MR, but if this occur, then it is always moderate to severe type of regurgitation. Now, when you compare the various Doppler technique, so on range resolution, continuous wave have a no range resolution, but pulse wave has a single gate range resolution, while the color flow has a range resolution with multiple gate. So you can identify exact location of the regurgitation or pressure gradient. Similarly, maximum velocity you will get with continuous wave, which is virtually unlimited maximum, but in the pulse wave it is limited by half of the sampling rate. And in the color flow you can get only mean velocity. Aliasing not occur in the continuous wave, but in pulse wave it is shown as a wrap around effect, and in the color flow you can you see as a color inversion and mosaic pattern. Sampling volume is large in a continuous wave while small in the pulse wave, while you can adjust in the color flow whichever you like to increase or decrease sampling volume. So, and the uses why continuous wave use in cardiology because its ability to display high velocity without aliasing, while pulse wave also used in cardiology but also other clinical application. and color flow is also used in cardiology along with peripheral vascular imaging. Thank you for listening.